Very, very happy today to have Frank Wong here. Frank is a postdoctoral scholar at Stanford right now, and he received his PhD and bachelor's in ECS from Berkeley. His research interests include signal processing, medical imaging, inverse problems, and optimization. And today, he's going to be talking to us about pushing medical imaging to new limits with massive computational methods. All yours, Frank.
Right. So yeah, thank you for the introduction. And thank you all for being here, even in these difficult times. And so I'll be talking about some of our work and potential future directions in medical imaging, and also combining massive computational techniques at the same time. Okay, so if you look at the last 10 years, there's really been an explosion of computational resources around us. Right? The cost of computing has drastically gone down over the decade. And so if you look at phones, or watches, or cars, or even headphones, each of them now has these really serious computing capability using multi-core CPUs or even GPUs. And they can also access almost unlimited cloud computing resources for a lot of its work. And since all of us have a phone, and maybe some of us have watches, as we can see from our daily lives, this tight integration of massive computational resources with these devices has really transformed how we use them, but also transformed how we design them as well. Now, in medical imaging, we're still not there yet. Because of regulation, the healthcare industry in general is pretty slow to adopt the latest technology. And there's also concerns about privacy and security that prevents us from connecting these scanners directly to the cloud, for example. And so in a lot of the cases, medical imaging is still limited right now in terms of computation power. And in general, this results in a fairly complicated workflow, but it also prevents us from correcting a lot of the artifacts. For example, motion artifacts, and we have to do a lot of approximation in our algorithms in order to make things work in a clinical reasonable time frame. But in general, this simply reduces the quality for a lot of these medical image devices. But this landscape is also rapidly changing. If you look into the news, every few months you would see that there's this collaboration between tech companies and also with healthcare companies and even medical centers to trying to integrate high-performance computing networks into these clinical settings. And they're happening now because of several reasons. One is that tech companies realizing there's a huge untapped market here that they want to take a share of it. But there's also because of machine learning or data science in healthcare, where hospitals want to do it. And to do it, you need some computing resources to do so. And so if you look at these news, so it seems more and more likely that the next generation medical devices or scanners will have some access to these massive computational resources that our phones now have. And it's also going to be likely that it will transform medical imaging. And so the question is, how will it transform? Now, one way to answer it is to look at other fields for inspiration, for example. We all have cell phones, and phones used to be pretty crappy cameras. It's 9 out of 10, you would probably get some motion artifacts. It's not as high resolution. It also is fairly noisy, used to be. But now, of course, things has changed. With massive computation integrated into pipeline, phones are sometimes now the best camera a lot of people have. And the way it has transformed mobile photography is that instead of reconstructing one image at a time, a lot of ways mobile photography now is done is by taking stacks of images, and then from that jointly reconstruct, and then create a perfect image out of it, right? And so massive computation has transformed mobile photography in this way. Computation has also completely redefined what it means to be a photograph, right? It used to be a photograph is something that's static, you print it out, and then you put it in the frame, and that's it. But now a photograph can be something that's dynamic. And it can be something that you can retrospectively change both in terms of lighting and in terms of contrast. And so it basically allows us to have new ways of looking at photographs. And finally, computation, of course, has allowed us to completely redesign the entire system. Instead of looking at this huge lens, trying to do everything at the same time, these phones now have multiple lenses, and allowing us to basically computationally combine the benefits of each lens in the back end. And so looking at this, and going back to medical imaging, perhaps we can also do something similar, right? And right now, a lot of the scans right now is still static, but perhaps instead of doing this one by one, just like in model photography, perhaps massive computation can also make scanners more reliable by capturing everything and then reconstruct the perfect moment out of it. And perhaps just like in mobile photography, massive computation will also enable new ways of visualizing the data sets, right? Allowing us to change the moment that we capture, but also perhaps changing the contrast based on the underlying physics. And finally, maybe perhaps just like in mobile photography, computation allows us to completely transform the overall system design, perhaps using cheaper hardwares, but also perhaps using multiple sensors together to create the perfect image. But of course, to do any of this, we can't just throw computing power at it and expect it to work. It really requires developments across the entire stack, right? You need theory to guide what kind of assumptions that your model is making, and also what kind of physical properties your system is exploiting. You need to design the overall system, combining hardware and software. You need to have fast algorithms such that it's possible in clinical settings to provide feedback in a short time. You need software implementation that allows us to adapt to the underlying hardware. And of course, you need the clinical translation part where you find the right clinical applications such that you can show people that this is indeed something that's possible and something that you want. And so with the emerging computing resources and increasing interest in data science and healthcare, I think there's tremendous opportunities right here for us to explore. But in this talk, I'll be focusing on a specific project in MRI, showing how all of these two can work together in leveraging these massive computational resources to push MRI to the extreme in terms of spatial and temporal resolution. But before I go into the details, I just want to show you a result. So here's a dynamic contrast enhanced imaging data set of a pediatric patient. And what I'll be showing is that during the scan, contrast agent was injected to the patient from the left arm, and it's going to flow through the body. Now, usually when this is done in the clinics, because the temporal resolution and spatial resolution is so low, technicians have to time the contrast injection very slowly, making sure they capture the right moment. And then there's also issues with respiratory motion, that there are a lot of tricks you have to handle. And so in general, these type of sequences are not very reliable in clinical settings, are therefore not used as much. But here, by simply pushing the spatial temporal resolution to the extreme where we can visualize the respiratory motion and the contrast dynamics, this allows us to simply basically press a button, scan for 5 minutes, and then in reconstruction, reconstruct the entire thing, and then you can sit in the room and then figure out which part you want. And so this is really powerful in overcoming a lot of the challenges in a clinical workflow. But of course, to get to this, there are some technical challenges.
Before you move on, could you just say more about how this contrast agent is injected?
Oh yeah, of course. Yeah, so these contrast agents, they're injected to the left arm usually, and it's flow through the body. And here in these videos, I'm showing that it's flowing through heart and going to the brain and so on. And so radiologists are interested in the contrast enhancement because it shows how the perfusion rate. And then from there, you can actually get a lot of the quantitative metric. perhaps not in this application, but one application that people care about is in kidney or renal imaging, where the contrast enhancement curves actually tells you how good your kidney is in terms of filtering blood. And I'll show the data set later on, and I can point to more detailed features that Right. So, yeah, so the technical challenge, right? The technical challenge here is that if you look at the data sizes, you can basically see that, right? We're essentially asking for about 100 gigabytes of image from just 2 gigabytes of measurements acquired over a 5-minute scan. And so this is clearly a hugely underdetermined problem. But even if we manage to address this, there's also going to be issue with the memory and also computation. How can we deal with this such that we can deploy this in a clinical setting? And so in the following, I'll be talking about two specific techniques that we've developed to address these issues. In particular, I'll be talking about a low-rank representation technique that we've developed that exploits the underlying multi-scale structure of the image that allows us to constrain the problem, but at the same time reduce the memory consumption. And second, I'll also talk about a framework of doing a stochastic and distributed reconstruction that allows us to leverage these massive scale computational resources to speed up the computation. But first, to make things more concrete, let me just give an overview of the MRI system. So in this talk, I'll be just treating the MRI system as basically just doing a Fourier transform. So we have the image there, goes through our MRI scanner, and then outputs the measurements, and those are measurements in the frequency domain, which we will be calling K-space. And so one thing about MRI, though, is that instead of observing the entire K-space or the frequency domain all at once, it actually takes lines of K-space line by line. And each line takes about milliseconds to do so. Now, while this isn't too slow, if you think about it, if you want to cover the entire volumetric K-space, this is going to be on the order of minutes. And so what this implies in terms of dynamic imaging is that to do any kind of dynamic imaging with sub-second temporal resolution, you can never really cover K-space fully. You always are going to have these partial K-space measurements for each frame.
So is there a hardware limitation why the scan cannot be any faster?
Mm-hmm. Yeah, so if you go too fast, you would first hit the peripheral nerve stimulation. So basically, you're switching magnetic fields, and so you would get currents in your body. And so that's just uncomfortable. But if you go too fast, there will be heating, and that's really dangerous. And yeah, so there are limits. People have gone down to 1 to 2 milliseconds, but that's really the limit. But what's interesting is that if you go to smaller patients, such as pediatrics, you can actually go faster because the switching part is actually it have more of effect for larger patients. And so there are also interesting developments in developing smaller scanners for pediatric patients, for example, where you can go even faster. Yeah, but that's a good question. Right, but what this implies in dynamic imaging is again that we can never cover K-space fully. But of course, if you know beforehand that you're doing dynamic imaging, you can design your trajectory for the sampling lines, such as these lines called spirals that would better cover K-space more uniformly. Now these are all just 2Ds, but you can also do this in 3D using these 3D cones trajectory. And people spend a lot of time trying to optimize for it. And so in general, they're really efficient trajectory to cover K-space in just a short amount of time. But if you don't do any constraints in your reconstruction, just taking these measurements and then try to do an inverse Fourier transform, this would be the type of images that you get. It basically look completely like noise and not really meaningful for any purposes, really. And so it becomes really necessary to impose some constraints in your reconstruction. And to put it more formally, essentially we're looking at a very ill-posed inverse problems. We have the case space that's only about 2 gigabytes, and we want to recover 100 gigabytes of image, and it's vastly underdetermined to go back. Now, while this used to be the end of the story, we now know that there are ways to deal with it. And one way is through compressed sensing. And so there are 3 components in compressed sensing. There's the incoherent sampling or incoherent sensing of how can you change your system such that it is somewhat randomized with respect to your representation. There's the compressed representation of how you can compactly represent your image. And finally, there's also the algorithmic part of doing a nonlinear algorithm reconstruction. Now for the first part, the incoherent sensing, it turns out you can simply take these 3D cones measurements, and then you can just randomly permute it, and that turned out to be a fairly good system for compressed sensing. They in general have a fairly low coherence. And so what's left is really deciding what's a good representation for these kinds of data set, and also what's a fast algorithm to couple with.
So each of these curves that you're calling measurements would also involve, so this is not like tomography where you would get a projection and so your curves can be straight lines. So what's the shape of this curve? What's the relationship between the shape of this curve and the hardware that's acquiring the measurement? And what constraints does the hardware impose on the shape of these curves?
Right. And so, so you're right, it's not directly a straight line, so it's not like a projection or a tomography. But in a mathematical or signal processing way is that it's basically taking the Fourier transform and then taking measurements point by point along this line. Now, how does the hardware constraint translate to the curves? And it's basically, it's almost, the hardware constraints basically constrains the speed and also acceleration of how fast you can go along the curve. And so ideally you would just go around as fast as possible, but then when you start out, you can go to the maximum speed, but afterwards you hit the acceleration. And then that's why these swirly lines are in general more efficient for MRI, because there's limits on the speed and also on the acceleration. Right. So let me just start with the representation. So by good representation, I mean something that allows us to use very few coefficients to represent these types of images, but at the same time general enough such that if it deviates from the perfect model a little bit, it still managed to represent. So if you stare at this video, as long as I did, you would find that there actually aren't that many types of dynamics in it. Most of the actions are concentrated around the heart. There's the contrast enhancement going through the heart, but there are also contrast enhancement in the blood vessels and some respiratory motion right here. But beyond that, most of the image itself is quite static and not moving over time. And so the approach that we're making here is that we'll essentially look at each of the dynamics, try to represent it as compactly as possible, and then add them up together as our representation. So I'll be just going through how we come up with our representation. So let's say you just have the background tissue and nothing is moving. Here's my cartoon representation of it. So there are many ways of compactly representing these types of images because it's just someone not moving over time. But it turns out one property that people use a lot is that if you vectorize each image into vectors and then stack them up and form this spatial-temporal matrix, it turns out it's going to have low rank, or in this case, in particular, it's going to be rank 1, right? And that's very simple to see because all the columns are the same, and so of course it has rank 1. But why is this sometimes preferable than other types of representation? Well, one reason is that if you have any kind of contrast variation, like the intensity changes a little bit over time, it still preserves these low rank property. And in MRI, that's very important because we often have a lot of fluctuations in the intensity, and so this type of low rank representation would still allows us to enforce these compressed representation. But this also points to the fact that it turns out low rank representation is also very good for representing contrast enhancement. And so here's my cartoon representation of the heart going through some contrast enhancement over time. And as you can see, if we again do this spatio-temporal matrix trick right here, it's also going to be rank 1. And so this shows that this low rank property is also preserved. Now, it turns out we can do even better, because one property that we haven't exploited here is that heart, like many organs, are pretty localized. And so it doesn't really span the entire space. And so, in fact, we can capture this by, instead of just imposing a low-rank constraint on the image, we can represent this spatio-temporal matrix into these low-rank block matrices. And so instead of having a rank 1 matrix, now we have a rank 1 block matrix to represent this, which in this particular example has 1/3 the coefficient to be represented. And so this basically allows us to get a more compressed representation for these type of dynamics. And this can be also generalized to blood vessels. For example, here I have blood vessel dynamics that are sparser in space, sparser in time. And we can also do the same trick of using smaller block sizes, both in space and in time.
So it's a little bit, I know this is a cartoon representation, but there's a 2D spatial structure which is relative locations of the pixels.
Mm.
That doesn't seem to have a natural way of mapping to the way it is at least depicted, which is all the things which are varying there are put together in some natural manner.
Mm-hmm.
So how does the relative structure get preserved, or is it not important?
So it's not preserved in the sense that its vectors rise in space,
Right.
but then the way the blocks are decomposed or partitioned, those structures are still preserved.
Is it because they're spatially close to each other and hence they just land close to each other?
Exactly, yeah.
Excuse me. I have a very dumb question. Can you briefly explain how the physics of MRI works? Like, what's the principle of MRI?
Uh-huh.
Yeah.
Right. So that's something I don't want to go fully into because I can give a very brief sentences describing it. Because like it will be a course, right? And then, but it has to do with spins, and then you have arc pulse to excite. But there's this analogy that you might find helpful or not. But basically, one way of thinking of how MRI generates signal is that it's almost like a toilet. And then the signal that you want is the water in your bowl. And so without doing anything, there's no signal. But then to generate signal, you would then excite by pushing flush the toilet. And then you get the signal coming out of it. And then, but this signal doesn't stay constant. It actually decays. And also there's like recovery in the toilet tank. And so each line right here, what happens is that you excite, you get signal, but then it decays. And so you have to have some finite time of sampling it. Okay, but then the signal that you get in the end actually just doesn't recover all the way. And so to get another line, you have to wait until a few milliseconds and then excite again and get another line.
So that's the limitation of the temporal resolution.
Right, in terms of sampling, in terms of the lines. Yeah.
When we recorded you on camera, you said MRI is equal to toilet.
Yeah. Right. Yeah, but I think that's one of the more intuitive way of explaining it. But yeah, it would take probably not a course, but like a week or 2 weeks of material to explain. Right, just finishing up here in terms of the representation, just putting everything together, here's our cartoon representation, and it looks more and more like the actual data sets. And the representation that we end up coming up with looks something like this, where we have this spatial temporal matrix, it's going to be low rank. But then the low rank factors have essentially different spatial temporal structures that span different parts of the space and time. So we look at this, and we decided to take a step back and see whether or not it's actually possible to do these kinds of decomposition in the first case. Now, in particular, we've abstracted the problem and look at the case where we had an input matrix where it's composed of low-rank components, but then also block low-rank components with sizes that's half the original matrices, and then also half and half, and go all the way to 1x1 blocks. And we call this a multi-scale low-rank matrix decomposition. And we wanted to study whether or not, even if we have access to these input matrix, whether or not it's possible to recover this, right? And so it turns out we look at some convex relaxation techniques, and we found that basically it is possible to recover the underlying components. And in fact, if you set your regularization parameters to proportional to the square root of the block height and block width, there's actually theoretical guarantees showing that you can recover the underlying components directly from them. And some of you might know is that there's also this low-rank plus sparse decomposition method proposed by other people. And this is essentially an exact generalization of that, because if you apply these convex relaxation of rank, which is nuclear norm, on these 1x1 matrices and sum them up together, that actually becomes the L1 norm. And so it generalizes very nicely from the low-rank plus sparse to these multi-scale settings. And these type of modeling is also useful not just for MRI. For example, we've tried this on surveillance videos where the goal is to separate the background from the foreground or different types of motion. And so the idea here is that the global low rank component would essentially capture the background, but then the different block sizes, the block low rank component would essentially capture different scales of motion. You have the people crowd moving captured by the 16x16 block, but then you also have the 4x4 blocks capturing essentially the legs and head moving. And so what this is showing is that this kind of modeling goes well beyond MRI, and we've tried other applications as well. But for the sake of time, I will just return back to MRI and show some of the results here. The important point here is that using these multi-scale low-rank model, we're able to represent this 100 gigabyte image very compactly. And indeed, when we apply it to these type of data set, we found that with just about a gigabyte of coefficients, that's indeed possible. Now, what I'm showing here is the decomposition. And one way these kinds of methods allow us to do is to look at the decomposition and figure out whether or not it makes sense or not. Now, indeed, if you look at the more local block sizes, you can see that it mostly captures the vessel dynamics. And so this matches with our expectation that the smaller block sizes should capture the fine structure. And the medium block sizes capture a lot of the cardiac enhancement. And so that also matches our expectation. And so all of these show that, or at least convinces us that this is indeed a pretty good model for these kinds of data sets. So with that, we can then plug it into the compressed sensing framework. And now we have the incoherent sensing system, compressed representation. What's left is to come up with a nonlinear algorithm that allows us to solve the underlying image. Now the issue is, though, is that with conventional algorithms, a lot of them are iterative algorithms that goes back and forth between the image and the measurement domain. But then what that means is that you have to basically operate on these huge 100 gigabyte image a lot of times. And so that's in general even very difficult for clusters because there's a lot of communication problem that you have to deal with. And so we have this compressed representations, and so one trick that we're thinking, or we've done, is that perhaps instead of solving for the image, we can just solve for the compressed representation directly, right? And what this allows us to do is to completely bypass the image and just alternate between the representation and the case space and never go to the 100 gigabytes image. This is also often used in a lot of other low-rank matrix completion algorithms. But here we're essentially applying this in our particular setting that have some very specific structures. And to make things more concrete, let me just go through the objective function. And that's the only math I have in my entire talk. So here, my objective function consists of the data consistency term on the left, and then the regularization on the right. I'm solving directly for the left and right singular vectors for each scale. And so usually you would solve for the image itself, but here we're solving for the compressed version directly. Then it goes through an embedding operator that reshapes it somehow, and then goes through sensing operator for each time point, which is, in this case, just the Fourier transform or the Fourier sampling operator. And then meets with the measurements, and then this consists of the least squares data consistency term. Now, this kind of factorization technique is often called the Bureau-Montero factorization. And turns out just by applying an L2 norm on the left and right singular vectors, that essentially is equivalent to the nuclear norm. But the only difference here is that this is a non-convex problem in general. And so it might be difficult to solve, but there's also a lot of theory that people have developed that under some idealized coherence condition that we can still be able to find the global min. So all of this is just to show that we're directly solving for the compressed representation so that we never have to go to a 100 gigabytes image, but instead just focus on the compressed representation. Finally, there's a trick that I still haven't mentioned, and that is to deal with the fact that we have many, many time frames. And so if we do any naive iterative reconstruction, we would still have to go through 1,000 times a Fourier transform per iteration. And that's also very expensive. But because this has this finite sum structure, and so I think a lot of you probably would guess is that you can then, instead of performing gradient descent or iterative method on this objective function directly, you can essentially perform stochastic gradient descent, where you pick one set of your measurement points, perform a gradient update, throw it away, and then you pick another one. And so the benefit here is that you never have to load all the data sets all together, but rather you can perform it in a streaming fashion and much more efficient. So this further reduces the memory consumption, and what's good about this is that it's very adaptable to distributed settings. Because of the structure of the problem, the right singular vectors over time are completely decoupled, and so we can embarrassingly parallelize them. And we only have to synchronize the left singular vectors. So we have the algorithm.
Sorry, one quick one. So can you go to the previous one?
Sure.
So the left singular vectors there, so what I'm not completely understanding here is you leave the left singular vector fixed for scale and only the right ones vary with time? So
right.
Only the right ones vary with time and the left ones are fixed?
That's correct, yes.
And then Rj in the regularizer is what?
Oh, yeah, so it's just the concatenation of
all the types.
Mm-hmm. Exactly. Yeah, and this is just to add some animation, but it's stochastic gradient descent. Right, and so we have the algorithm, we have the compressor representation, we have the sensing system, but we also need something else. We actually need fast implementation to make things work. And so over the years, we've actually released and implemented a lot of these open source software tools so that people can do a lot of the fast computation here for these reconstruction. And so one thing that we found is that it turns out a lot of the operations that we need here, such as a wavelet transform or non-uniform fast Fourier transform, they don't really have a good open source implementation. And so in order to do what we need to do, we actually implemented all these algorithms directly in CUDA and then also in NPI. And so in addition to these fast functions that we implemented with GPU and CPU support, we've also created this almost abstraction languages for how to perform iterative algorithms. In particular, it has the structure of separating the algorithm, the linear operators, and the proximal operators. And then by defining these classes with a lot of the properties, allowing us to prototype it very efficiently. And so over the years, we've seen an expanding user base using our toolboxes. One of them is called BART, Berkeley Advanced Reconstruction Toolbox, which is C and C++ based. And then there's also another one that we recently released called SigPy that's more tiered towards Python. Great. And so it's really combining all of these together that allow us to create the images I've shown before. And let's see. And just to point out some of the details more here. So in the beginning, you can actually, because we resolved this image data set with high temporal resolution, we can see the respiratory motion. And then what's happening here is that the contrast flows into the right ventricle, and then to the lungs, and then to the left. And so this is something that only with high temporal resolution can you visualize this, and this is not possible with a lot of the existing techniques. And because it's volumetric, you can also see it in another way. And one thing that's interesting here is that if you look at the person's back right here, you can see that the patient actually moves a little bit when the contrast is injected. And even though that's not directly explicitly captured in the model, we're still able to visualize it.
The fact that there are so much changes in these images across time, but it's still relatively sparse, right? You're saying that you need a gigabyte of parameter space, essentially.
Right.
Could you, is it because somehow there's only local movement or some other structure? What is the insight behind
Right.
that?
Yeah, exactly. So there's like a lot of the movements are local, so that's the multi-scale structure you're trying to capture. But then another thing is that even a lot of the dynamics are just intensity changes. And so structurally, it doesn't move at all. And so if you know beforehand, like this is the heart, of course here I'm doing block sizes, then essentially over time, you need very little update in terms of like signal innovations. And this is also one reason why it's able to compress by a lot.
So is there a notion of, let's say, innovation in this, or entropy rate of this thing is actually much lower, you're saying, compared to actual?
Exactly. Yeah.
I see.
Yeah, but we haven't quantified like entropy, but like, in terms of data sizes, 1 gigabyte versus.
So, I mean, this is related to Ashu's question. So, the model is assuming, at least it's best suited for when there is no motion and there is only intensity change per pixel, independent intensity change. Perhaps there is some correlated structure in spaces, but really there's no need for structural correlation even, because the pixels that are blinking together could be arbitrary pixels and the model is equally valid.
Right.
But in the video that you're showing, there's actual motion of the heart. There's in a biological setting, a part of the dynamics is actually motion.
Right. Yeah. So that part I won't talk about here, but that's something I've worked on and extended. Like you can imagine the blocks actually shift over time, and so that will allow us to capture the motion. But you're exactly right. In this kind of model, it just assumes intensity changes. But what's interesting is that even with this, as long like all of the examples I've shown, they're rank 1. If you allow slightly more ranks, it's actually able to capture these respiratory motion. And one reason is that if you just alternate between 2 phases, for example, then this is going to be a rank 2, and so that's one way of capturing that. We actually do have work extending that, and that's a really good observation.
I guess that's very important. So in the picture that you showed of background and foreground, people are certainly moving across the whole image, right?
Right.
So
Mhm.
there you would need some of that.
Right, right, yeah. Yeah, so these kinds of models we're just starting, but again, yeah, I agree, like extending that along that direction would be very important. But it still do pretty well with motion. So here's another case with more motion. And so you can see from the outside, like the patient actually completely shifted to right. Now there's some artifact because we're assuming this intensity variation model, but it still managed to capture the shift pretty well. And if you go inside, the same thing also happens. Right? You can see this. So you're right that it's not capturing motion directly, but it still is pretty robust to it. And that's why a lot of these blowing methods are often done in these imaging tasks. So we're pretty happy about the image quality in general. And so since last year when I started at Stanford, we've been integrating our reconstruction pipeline into the Stanford adult and children hospitals. We started with lower temporal resolution, but then gradually increased. And just over last year, we've collected already about 500 cases. And I've collaborated with a radiologist fellow, Sydney Holmes, and to compare the proposed method with the conventional method. And one thing we found is that in general, it has improved image quality. There's in general less noise and less grainy looking artifacts. And there's also noticeable improvement in delineation of anatomical structure.
And when you say here conventional, that corresponds to conventional scanning and conventional algorithm, or what?
Right. Yeah, so it's the conventional in terms of what they use clinically right now, which is with a different sampling and a different algorithm. But conventional sensing doesn't have these computation issue, and so it's relatively easy to do. That's why they use it. Cool. And so that basically wrap up my current work. And so in the following, I want to talk about some of the future directions and some of the stuff I'm doing right now and so on. And so as many of you know that when we start working with real-world data sets, new ideas and new challenges would emerge. And so some of them are still related to my current project or the project I've presented. But in general, I will, along the way, also point to more general future directions. And in particular, I'll point out several, I'll highlight some of the challenges and opportunities. One of them is how can we learn from undersampled data sets? We've just seen that just from last year, I already got 500 data sets. How can we leverage that to improve image reconstruction? And then there's also challenges in visualizing these large-scale data sets. How can you look at all of them at the same time and figure out what's interesting? And finally, I'll also point to interesting directions in the field, and that leveraging some of these massive computational techniques, but combining it with low-cost hardware to improve certain aspects of medical imaging. So one opportunity coming from clinical integration is that, of course, suddenly we have access to all these hundreds of data sets, right? And most of the time after reconstruction, they're just sitting there doing nothing. And they kept on accumulating over time. And so it will be great if somehow we can actually leverage them and then use them. The challenges, of course, is that all these data sets are undersampled. I've just gone through a lot of time telling you why it's impossible to get fully sampled data sets. And so they have to be undersampled, right? That's like the physical limit. And so we don't have ground truth. How can we still leverage them to improve reconstruction? And so this is something that we've been thinking a lot about, and we don't have the final answer on it, but one way of approaching this problem is to treat it almost like a dynamic image reconstruction, where instead of having measurements from just one data set or one frame, we now have essentially measurements from different patients. And one way to phrase this is that you almost want to do this joint reconstruction across all these patients and then find a common compressed representation that allows us to reconstruct all of these images the best as possible.
What's the thought behind combining across patients? Like, what's the seed of this idea? Why do that?
Right. So our thinking is that it's almost you have a distribution of patients, and then each patient gives you certain measurements through our scanner, and then each one is undersampled. Now our goal is that future patients come in, we can still get these undersampled data sets and reconstruct it better. And so one way of doing that is that with our distribution or acquired data sets, learn compressed representation out from that, and then use that for the future patients. So maybe giving us a particular example makes more sense. So here is a compressed representation that we've been looking at, in particular the convolutional sparse coding model, where we essentially model images as filters convolved with sparse coefficients. So very similar to how it's basically exactly the wavelet transform model. But in convolutional sparse coding, instead of having fixed filters, you're also trying to learn or optimize for the best filter. And so if you have a given data set, you would then solve this convolutional sparse coding problem of these data sets. And then once you have a new data set coming in, you would use these learn filters and then use it for reconstruction. And so what I'm showing here right now is that in data sets where we have ground truth, we can compare conventional compressed sensing using L1 wavelet, and then also convolutional sparse coding trained on fully sampled data sets and trained on undersampled data sets. And as you can see in the zoom-in portions, these convolutional sparse coding models in general has a sharper response here and showed much better delineation of these edges compared to the regular compressed sensing. And so this shows promising results in leveraging these undersampled data sets to improve reconstruction. But of course, we more recently we have been trying deeper and deeper models. And one thing in particular is that we looked at these deep unrolled models, where essentially you take conventional compressed sensing reconstruction, unroll them, and then construct a neural network architecture from them. And so we take these neural network architecture and then put it into a GAN training framework, and then manage to reconstruct the following images out of these undersampled data sets. And so these are still preliminary results, but as you can see, if you look at these kind of regions, in general, it's much sharper than the regular compressed sensing results. Now, one thing that we found in our experience is that these unrolled neural networks, where you interleave neural network and data consistency, in general, provides much better performance than a lot of the conventional like UNet or direct neural networks that we've been experimenting with. And one benefit of using these unrolled neural network is, again, that because you have data consistency built in, they're often more reliable. And so these are some things that I've just been working on, and all of them showed promising results. And there are also a lot of methods, some in this department and some in other schools as well, trying to look at this problem of learning from undersampled data sets. But I think this is still an early stage for these kinds of problems, because a lot of things are still unknown. What are the assumptions going into these models? What are the trade-offs? Like, if you undersample by too much, is it still possible to do a lot of things? And so I think in general, there's a theory aspect, but there's also how to develop algorithms that allow us to very effectively learn something useful from these undersampled measurements becomes a very exciting direction. And one thing I've thought about it is that this is almost an extension of compressed sensing, where instead of just designing the system for one image at a time, we're essentially designing a sensing system for a population of images and trying to essentially get these incoherent measurements from all of them at the same time. So I find this very exciting, and it's something I'm interested in. We'll continue to work on it in the near future. So switching to another topic, one challenge that we faced in clinical translation is how to visualize these large-scale data sets. Now, one of the challenges really comes from the insistence of radiologists of storing these images into lossless formats. If you've dealt with image compression in the hospital setting, you know that they, in general, don't want to do any kind of lossy compression and just want to store them directly into these DICOMs. Right? But when you think about it, it doesn't really make sense because in compressed sensing, we've already compressed it down to 1 gigabyte, and then now we're decompressing it, storing directly into these 100 gigabytes DICOMs. And so this is one reason that prevents us to really deploying our algorithms in clinical settings, because it completely overwhelms the hospital infrastructure. And so instead, we do something that actually makes sense, which is instead of going to DICOMs, we try to visualize directly from these compressed representation. And so it's very similar to how when you stream Netflix videos, instead of downloading the entire movie, decompressing it, and then look at it, you actually stream it bits by bits, and as you scroll through, it will only stream the part that we're interested in. So very similarly, but instead we're dealing with these multidimensional data sets and also with these customized compressed representation. And so we have to essentially design and also implement a lot of these operations that allows us to operate directly on the compressed representation. And what I'm showing right here is that on these low-rank factors, for example, you can directly slice the compressed data and to reconstruct it directly instead of downloading all of them together. And there are, in general, several operations that are different for Netflix streaming, where in medical setting you would like to do perhaps averaging, interpolation, and then there's also surface rendering that would require to operate directly on these large-scale data sets. And so the idea is very simple, but it's really just a lot of implementation. And here's a proof of concept that we've done that showing how you can visualize these high-dimensional data sets by directly visualizing from these compressed representation. This may look very natural to you, but what's important here is that it's basically just running on my laptop. And it used to be impossible to really visualize these data sets, and now on my laptop we can do so. And so this is something I think it's also very interesting, is that the overall concept here is very simple, but it really addresses a huge pain point for the radiologists. And we're now being asked to extend this to other compressed sensing applications as well. But I see this really as a first step of a bigger direction. And so in general, when we look at medical imaging, we often just stop at the reconstruction and when we get the image, and that's it. But really beyond that, there's a lot of steps after it, right? And so before there's acquisition, reconstruction, but then there's also visualization and then analysis, like how you segment certain parts, how you do quantification. And right now, all of these tasks, they're pretty much separate. And so, like, even though we do a lot of compressed sensing and reconstruction, visualization doesn't really take account of it. And then there are a lot of opportunities here to really combine these tasks together, right? Visualization should perhaps know about the imaging physics, and what this will allow us to do is essentially adjust the contrast in backend. Analysis, like segmentation, should probably also know about imaging physics and reconstruction, because if we change anything in there, it's going to propagate through analysis. Now, right now, they're all decoupled, but I think by co-designing the overall pipeline, there's huge opportunity here to really improve in all of these fronts. So finally, I want to talk about potential directions and new system designs in MRI. And so MRI hardwares haven't really changed in many years. And all of the work I've shown basically operate on the same expensive magnets or same gradient coils and same RF coils. And with these massive computation, we've shown that we can reconstruct these great images like high dimensional and whatnot, right? And that's really cool to see, but in a lot of settings, perhaps instead of these high dimensional imaging, you're perhaps more interested in just good enough image for some application. And so perhaps in these settings, you don't really need the expensive hardware. You can perhaps leverage and use some of the cheaper hardware that has other benefits, such as being portable or not being that magnetic, and so you can go near to it. So this is something a lot of us in the MRI community are thinking about, and there are increasingly momentum and also attention in the community trying to look into these kinds of problems. And so for example, in our NU conference this year, but going to be delayed because of the virus, there's a session here that tries to look at how we can essentially bring MRI to low resource areas by completely redesigning the hardware and using these low-cost scanners. And it's not just academics working on it, there's also startups interested in it. Here's an example of a hyperfine MRI scanner. And so these kind of scanners, they're still just recently got FDA approved, but instead of having a usual 1.5 or 3 Tesla, these kind of scanners try to use ultra-low field, which is about 0.064 Tesla. And what this means is that the system is very portable, but also means that you can go very next to it, and you can have your phones and belts in it, and it's still fine. And so there's a lot of interesting things, but the thing that caught my eye is, of course, the cost. It's only about 50K, which is somewhat affordable. Right. But the only downside here is, of course, that your images now look completely very noisy and also low resolution. But the thinking here is that perhaps leveraging a lot of these massive computational techniques that we've developed for these expensive hardwares, perhaps we can drastically improve this and make this useful for certain applications. So with that, I'd like to wrap up. So I focused on MRI, in particular dynamic MRI, to illustrate how leveraging these massive computational resources can allow us to push medical imaging to new limits. And I've shown that this required developments across a whole range of topics, from theory to system to algorithms to software to, of course, clinical translation. And several things in particular, I've shown that how I've developed techniques that allows us to achieve higher and higher temporal and spatial resolution, allowing us to get better high-dimensional imaging. I've also pointed out interesting directions in leveraging undersampled data sets for these kind of purposes as well. I've also shown potentially new ways of visualizing data and perhaps coupling all the tasks over the clinical workflow. And finally, I've also pointed out interesting directions in potentially new system designs where you can leverage these massive computation and couple it perhaps with these cheaper hardware and create something that's different. And with that, I'd like to thank all of you for being here. And, yeah.
In your reconstruction there, let's say of this video, are you able to preserve like real temporal effects in the sense like that beating heart? Are you able to analyze and determine the actual heart rate by looking at the contractions, or is this sort of like a fake time? I guess the question is, are you able to preserve this in the reconstruction, the actual biological time?
Right. So yeah, so I mean, like I'm collaborating with radiologists, and they look at it, and there are certain ways that is able to verify whether this is real or not. So this is trying to reconstruct it in real time, but I guess the question is whether or not it actually preserved the actual dynamics.
Right.
And so for the task that we're looking at, it seems to be doing so. But one thing that you mentioned is that the heart is actually not beating here because our temporal resolution is not fast enough for that. So in that sense, it's actually not preserving cardiac, but it is preserving respiratory. And that's actually one remaining work, or one, I think there's a lot of work to go into here, is to push this even further and get the cardiac and everything into real time. Yes?
And so one concern that has always been in my mind in using, for example, these learned